Hello, Sonia and Janet. Okay, so today we have our guest lecture, which is from Dr. Riza Mir Mokhtatei. So Riza was my former PhD student, and right now Riza is a senior research scientist at the Concrete Lab in Civil Engineering Department at UH Manova. Okay, so Riza will give a presentation on normal concrete materials. Basically, it's called alkali activity concrete or geopolymer concrete, which is a concrete, I think I mentioned in the class, using no cement, but can achieve very high performance. And at the same time, the cost may be comparable, even lower than conventional concrete. Okay, so Lisa, okay, please.
Okay, thanks for one more time for having me. I'm happy that I'm in your class. So as Dr. Shen explained, I'm going to introduce a novel concrete material. We typically call it geopolymer concrete or alkali activated concrete, and also its application. So today I'm going to cover, by starting with an introduction, a history of this material, the methodology we use in our study, and some results that we've got already, and also we are continuing working on this type of material and the properties of it, and then some possible applications for this novel material. If I ask you, what is the most widely used material? You might know the answer, maybe all of you. So the most widely used material is water. But if I ask you in this way, what is the most widely used material after water? What will be the answer? Generally, it's a general question. I'm not talking about the construction materials. What is the most widely used material after water? Any idea?
I've heard it's sand, natural materials, and we
Oh, yeah.
use
Any
a lot of sand in concrete.
ideas? So you got it. Yeah. So the concrete. So just to put it in the perspective, if we put all the construction materials rather than concrete on one side, I mean all the metal, the glasses, aluminum, wood, all the construction material on one side, the consumption of concrete is 3 times of all of them. We could expect it because we can see concrete almost everywhere, in driveways, in patios, in parking lots, in buildings as a form of columns, beams, slabs, foundations, shear walls, in bridges, structural and non-structural components and elements of bridges, and these nice dams out of concrete, all of them, fabricated with this material, concrete. But to fabricate this material, we need cement, water, sand, gravel, and done. But today I'm going to focus more on the first component or ingredient of the concrete, that is cement. You may see this statement in journal papers that publish about the concrete materials. We need a sustainable alternative for cement. But why? What's wrong with cement? What's wrong with this type of material? We have some challenges. We have climate change problem. 8% of CO2 emitted by a human being is just for the production of cement. We are producing 4 billion tons of cement each year. And by assuming that the production of 1 ton of cement is equal to the emission of 1 ton of CO2, it means that we are emitting 4 billion tons of CO2 into our environment. If I want to put this in perspective, Imagine that all the cement industry gathered in one country. And then we want to rank different countries and then see which country is responsible for the environmental pollution more. The first one is China. The second one is United States of America. And the third one is cement industry. Challenge: the cost of cement. According to this, price listing of a ready-mix concrete that I get in 2018 here in Hawaii, almost 1/3 of the cost of concrete is for purchasing cement. Challenge: our infrastructures in United States are old. According to ASC, American Society of Civil Engineering, since 1998, the infrastructure grade, the Stockton-D grade, it means that we've done almost nothing for repairing our infrastructure. And based on the report released by ASC this year, 2021, we need $2.6 trillion investment by 2029 and $5.6 trillion by 2039 if we want to fix these infrastructures. It means that we need a lot of material to repair and replace this old infrastructure. We cannot ignore concrete, the conventional concrete. We will definitely use concrete for the repair of infrastructure, but we need a substitute. We need a sustainable substitute for this gigantic amount of material that we need for our infrastructure in the US. Challenge: ecological impacts. For production of cement, we need limestone, you know better, silica, aluminates, ferric minerals, and other material and minerals that we need for the production of cement. It means that each year we are extracting 3 billion tons of material, and we are digging gigantic holes into our planets just for the production of cement. Challenge: we have industrial waste. We have aluminum factories that release these toxic red materials, that we call it red mud. These guys in this village are living beside this toxic material. It's a real life. We have some power plants that burning coals. So coal ashes, fly ashes, whatever we call it, is a waste material. We just landfill them. We just stock them on top of each other. And also steel factories are fabricating some byproduct of them that we call the slag. We don't know what to do with this material. Fortunately, we have some solutions for them. We need to find a substitute for cement. Pozzolanic materials. We can replace some percentages of cement, 10%, 20%, 25%, by some pozzolanic materials, pulverized fly ash, slag, rice husk ash, and silica fumes. Specifically, some material that has reactive silica in it is a good replacement for some percentages, not 100% of cement. Geopolymer concrete is a type of material that we don't use cement anymore in it. But the key point is that for production of geopolymer concrete, we need something that has pure silica and alumina in it. And then we can get something like ceramic, something very strong. But these materials are not cheap. The last solution is using alkali-activated materials. Scientifically, geopolymers are subset of alkali-activated materials. For fabricating alkali-activated materials, we can consume any waste materials that has alumina, silica, and calcium in it. So today I'm going to focus more on this material, alkali activated materials, or possibly I call it AAMs. For this type of concrete, we need the waste material, but not any type of waste material. They should have enough reactive silica, alumina, and calcium in it, like fly ash. We need some chemicals, and then a little bit of water to dissolve this, and then this solution dissolve the waste material, and then by this process, we can have enough of silica, alumina, and calcium in it. The rest of them is very similar to a normal concrete. I mean, the sand, gravel, and then exactly the same material that is formable and then hardened because of the reaction of it. We need some definition to understand the difference between this type of novel concrete and then compare it with a normal concrete. Alkali activation is a reaction of a solid alumina silica that from now on we call it precursor. That could be metakaolin that is pure, that has pure alumina silicate, or any type of waste material under alkaline condition, alkali activators, to produce hardened binder. So we typically use two terminologies: precursors, that we can call it powder, like a slag, fly ash, calcine clays, natural pozzolans, red mud, rice husk ash, and alkali activators, or we can call it chemicals, like hydroxide, sodium hydroxide activators, or silicate activators. Is a combination of silica and then the sodium or potassium, typically the sodium one. So we need some powders that has silica, alumina, and calcium in it, and we need some chemicals that could resolve the powders and then release these silica, alumina, and calcium, and then we can have the reformation of strong molecules, and it hardened, and we can get compressive strength, for example, out of it. But here in Hawaii, I discussed that United States has looked for substitutes, sustainable substitute for the cement, for the normal concrete. But specifically in Hawaii, we have something more than that. We have more challenges. We are not producing cement directly here. We are importing cement. And we also have some power plants that generates fly ashes, the waste material. And then superior properties of AAMs motivated us to produce alkali activated materials instead of normal concrete in the state as a local production. Just to give you some idea, the origin of this material was back to 1908 in Germany. So the reaction patented by Kohl, a German chemist. And then in 1940, Purdon developed it as activated slag by sodium hydroxide and calcium hydroxide. And 19 years later, in 1959, Glovsky in former Soviet Union in Kiev used the alkali carbonate activation of metallurgical slag. And then you may hear this name, the Davidovich, that initially in 1982 patented the alumina silicate base formulation and then call it geopolymers. So geopolymers are something like ceramics, if you want to have something in your mind. It's very strong, it's super strong. But as I mentioned, because we need pure silicon alumina, we need to purchase something expensive. So it is not a focus in our discussion today. But the project that we have so far historically, in 1958, we have a parking structure in Belgium out of alkali activated slag. In 1994, in Russia, we have alkali activated slag again. We call it this, alkali activated concrete. And in Australia, in 2009, they started fabricating some precast concrete out of alkali activated materials. So it is not something new, but scientists are working on it to enhance the property and then commercialize it more and more. Here in Hawaii, I think in 2014, before I came here, Dr. Shen and some students work on geopolymer concrete and then pour it in downtown Hilo. And then we monitor the strength of the sample we got from the hardened part of this concrete, and it was amazing. So the compressive strength, the durability was pretty good. And then we motivated to work more on it and then produce it out of the local Hawaii fly ash. In this path, we analyze some raw materials that I will, discuss it in more detail in next slides, and then monitor the dissolution by some techniques. The selection of material and mixing technique was the third step we've taken as our methodology, and some tests to make sure that our design with this new material are working well. The first step was analyzing the raw material. So typically, if you want to use a new material, you need to know the chemical composition of it. So we use XRF, X-ray fluorescence, if you want to know the percentages of different components of any material. For example, specifically for cement and the type of precursor that I'm discussing today, we are focusing on the percentages of silica, alumina, calcium, and other components that might contribute to the reactions by XRF. But what we've done more was study the precursor and the reactions more by XRD, by the combination of XRD and XRF, and we could get the quantitative study on the amorphous and crystalline phases of precursors. And also we employed a novel technique using Raman spectroscopy instead of the combination of XRD and XRF. That sample preparation was very hard. The reason why we refer to something new was that the sample preparation was very hard, and by Raman spectroscopy, we could, do the same thing, faster and easier. But I'm gonna, explain it better in next slides. And then based on the complete phase analysis, we could generate mixed proportioning. And then, so in this step, the monitor of dissolution process, we studied both crystalline and amorphous phases, amorphous part of powders. So what I mean by crystalline, in this case, in alkali activated materials, we have some components inside our waste material that cannot be dissolved by chemicals. It means that if I increase the concentration of chemicals, that means that I'm increasing the price and cost of the concrete. I cannot dissolve this part of powder, the waste material. So it is important to know how much of my powder, of my waste material, is not dissolvable and how much is amorphous. It means that it could dissolve easily and fast. And then I can, develop the concrete easier. Investigation on the dissolution process could help us an appropriate mixing procedure and timing. So the timing was very important for us. For example, for type F fly ash, because it had higher percentages of amorphous, the guide that could be dissolved easier, was very high. It means that once we introduce the chemicals onto class F fly ash, it dissolves very fast. And it doesn't matter if you, for example, introduce chemical number one and then chemical number two, or mix one and two and then introduce it, it dissolves very fast. But for example, for some waste material that we had in Hawaii, we had many impurities. And it was very important to know that we need to, for example, introduce chemical number one and then wait for a specific duration that we got from the monitoring from Raman spectroscopy, wait for the chemicals to dissolve it well, and then introduce chemical number two. So the timing was very important, specifically for our material in Hawaii. And then we could adjust the concentration of alkalis because the chemicals are very expensive. So we want to, compete with normal concrete. As I mentioned, the cement is very expensive. But if I want to produce something cheaper than normal concrete, we need to optimize and minimize the chemicals that we're going to use. So this timing and this monitoring help us to minimize the concentration and the amount of the alkalis. And then by gathering the information from the last two steps that I mentioned, we could, step further to next steps. If more than a specific time is needed, because we could, we understand that we need to have separate phases for the introduction of the chemicals, chemical one and chemical two, so we can adjust the, timing. If we need more time, doesn't matter. We just, wait more for the chemicals. For chemical one, that is sodium hydroxide, for 5 minutes, more than 5 minutes, or whatever we need, and then introduce the rest of, the ingredients. And then the amount of calcium, the calcium is very important for the setting and hardening of alkali activated materials. So the adjustment of calcium, the amount of calcium is very important. We need to think about it. For example, if I use type F fly ash that has lower percentages of calcium, I had to pre-mix it with slag or something that has higher percentages of calcium, and then introduce the chemicals. So I can adjust the ratio of silicon calcium and aluminum calcium, because these guys are very important in formation of 3D molecules of geopolymer concrete, or alkali activated concrete. Specifically for precursors and waste materials with high impurities, we followed these steps. We figure out that if we dry mix a precursor, if we have 2-3 types of precursor with different percentages of alumina, silica, and calcium to optimize it, we need to dry mix it first, and then introduce the first chemicals, that is, sodium hydroxide, and then we can add aggregate and then mix it. And then as the last step, we can introduce the sodium silicate activator, and then we've done. So before our study, what we've had in the literature review, the scientists mixed the chemical number one and number two initially, and then introduced it to the precursor, to their materials. It works for a type of precursors that has not have impurities. They are pure silica alumina in it, like class F fly ash. But in our cases, because we had many impurities, we separate chemical one and chemical two, and it worked pretty good. After we've done with the initial production of our concrete, we started some tests on fresh properties like setting time, initial and final setting time, the workability, the slump loss, and then hardened concrete, compressive strength, whether the tensile and flexural, and some durability tests, including the leaching test, because we are using waste materials. And it is not supposed to use something toxic that could easily leach out, came out of our concrete into our environment. Imagine that we are pouring foundation with our concrete, and it is adjacent to soil, and soil and water could approach to our concrete and dissolve our some bad guys from the surface of the concrete, and then these guys could travel to our environment. We don't like to have something after using this waste material. So what we are doing, and we are continuing studying on it, is some leaching tests for our environment to make sure that these waste guys remain in the concrete securely and will not appear in our environment later. As I mentioned, we have some XRF study. So the procedure for the XRD, I mean, the sample preparation was time consuming and hard. We need to, mix the powders with some waxes, well, and then compress it with some machines to make some pellets, and then put these pellets under the XRF machine. But the result was fantastic. So I had, different types of waste materials and powder that use XRF, and then got these numbers. This table and these numbers and values show, for example, for H power ash that I got from the H power plant has, for example, 81%, 0.81% alumina, 2% silica, and 40 something percent calcium. And the same for AES fly ash, the type F or class F fly ash, slag, and the cement. For example, as I mentioned already, I have to have enough of calcium if I want to generate good AAM, alkali activated material. As you can see here, we just have 2%, less than 5% calcium. It means that if I want to produce geopolymer concrete or alkali activated material out of type F fly ash, I have to add something like a slag that has enough percentages of calcium, and then good amount of alumina, good amount of silica out of the fly ash, and enough amount of calcium out of a slag, I can get good property. I can also generate alkali activated material with cement, but it's not reasonable because we are replacing it. We are, starting to get rid of this material, so we don't use it anymore. Any questions so far? I'm just talking. If you have any question, idea, comments, let me know anytime. So using XRD, we had some crystalline phase analysis. So we had to know that what percentages of our powder could be dissolved easier. In case, for example, for AES fly ash was 53%. It means that half of the AES fly ash could dissolve easily, and almost half of them could not. It means that we have crystals that could not easily dissolve by our chemicals. It means that if we want to dissolve it well, we need to introduce some chemicals with higher concentration or weight more for some bad guys, for example, like calcite or sulfate, components of this waste material, because these, guys absorb the water of the mix, and we couldn't further the mixing procedure of the alkali activation. So we learned that by introducing chemicals in elongated period of time, for example, more than 5 minutes, with a constant concentration, we have more and better dissolution, and then we could generate a very good alkali activated concrete with local AES fly ash. Again, we had a long procedure for sample preparation, so we need to use some micro to make it powder, some micronizing procedure to make it powder and then dry it. Um, Another problem for drying the powders was that we didn't need to use heat because heat we would change the property of our concrete and we didn't like it. So we need a lot of hours to put it in this vacuum oven. Is a specific type of oven. It was hard to prepare some sample for XRD, but the result was fantastic. So exactly, for example, we know that this type of precursor had 36.6% of silica. And after complete phase analysis, we figured out that just 22.59% of the total powder could be dissolved and then release the silica. It means this. So the amorphous column of this table shows the numbers of silica, alumina, and calcium that could be easily dissolved by a normal concentration and normal amount of chemicals. And it was very important for our study. But we found that if we use Raman spectroscopy instead of XRD and XRF, we can, get rid of frustrating and time-consuming sample preparation. So any sample, any small sample of powders or the hardened concrete could be easily put under the microscope of Raman spectroscopy, and then we could get the spectroscopy and the results. The only problem was that it was not like XRD and XRF because it's not a common technique for studying the concrete and the cement. It is designed for something else. So I had to wrote some codes in my lab to employ this technique. I mean, the Raman spectroscopy easier. And then after using this, we could, for example, say that exactly 1% of this powder has quartz. You know that quartz is a crystal and could not easily dissolve by chemicals. So it was important to know the exact numbers and quantitative result of these numbers. And monitoring of the solution, as I mentioned already, was very important. So here is an example that I had a powder and then I labeled them. For example, number 1, this region is a glassy alumina silicate. So is a combination of alumina and silica that could dissolve easier. And these peaks are the crystals, different types of crystals. For example, 3 and 4 is crystalline and pure sulfate. And this number 5 here is calcite. So it is important to know what these peaks are. And then I introduce a chemical number 1 that was sodium hydroxide into it, and then monitor it. It means that I set up the device, I set up the Raman spectroscopy to get the spectrums after 1 minute, 1 minute, and then 10 minutes, 10 minutes, half an hour, and 1 hour, 1 hour for the whole 24 hours. And then I got something like this. So as you can see here, because the concentration of the chemicals was very high in this example, all the crystallines, all the peaks, and amorphous phases of this powder is going down. It means that they are dissolving. And then I monitor it for 24 hours to get, for example, what's going on inside the concrete when I introduce the chemicals over time. And then I could get the exact timing and procedure, mixing procedure for any specific type of precursor. For example, if we have, powders, waste material like AES, fly ash with high impurities, with some components that I don't like. I like silica, alumina, and calcium, but I don't like, for example, unburned carbon. and or sulfate components. So I have to know that what is the exact and optimized time for the solution process. When I introduce the chemical number one to our powder, how many minutes do I need to have the optimized dissolution? And then I could get this. Just to compare the alkali activated concrete with the normal concrete with the conventional concrete, I took these numbers. So here is a mixed design for 5,000 psi compressive strength. So as you can see, we need coarse aggregate for both of them, almost the same numbers. We need sand. Regarding the water, as you can see, we need less water for the production of alkali activated concrete, not only for the production, but for the curing. You know that right after the concrete set, the initial setting or the hardened, the final setting of the concrete, you need to introduce water because the hydration of cement and water needs water. But for alkali activated concrete, we do need it, but not that much. We just need to, spray a little amount of water and then cover it with a plastic sheet. That's enough. That's enough curing technology for alkali activated concrete. And then we are using, for example, fly ash instead of cement, and then some chemicals. Chemical number one, that is sodium hydroxide pellets. Chemical number two was sodium silicate. And we also need some admixtures to control the setting time and the workability of this type of concrete. And the total density of the concrete, depending on the mixed design, almost the same as the normal concrete. And then we got the amazing result out of it. So we could just use 100% AES fly ash without any cement, without any other type of material, just the fly ash, just Hawaiian fly ash. And then, as you can see, we could get almost 4,000 psi after 3 days, and then 5,600 psi after 28 days. You know that for structural concrete, after 28 days, we need around 4,000 psi compressive strength. And we could get this number after 3 days. So very fast. So you can consider, concrete repair, for example, or concreting in cold weather. It harden, it get ultimate desirable compressive strength very fast after 3 days. If we, um, design the concrete to set fast. And also we use the H power. So H power ash is I can say it's a rubbish ash. So in H power, we are burning rubbish. So we are not expect to have something valuable out of rubbish. So we just encapsulate it. We just push it inside our alkali activated concrete. So we use 70% slag and 30% H power ash and get good result out of it. So 28-day compressive strength, that is a criteria for our design, is almost 6,000 psi, higher than 4,000, that is a normal one. And then by using 70% class F fly ash and 30% slag, we could get super high compressive strength that was 20,000 psi. I was talking about 4,000 as a normal structural concrete. We can get something 5 times of normal structural concrete regarding the compressive strength. Or if you are Pascal guys, it is around 140 megapascal. But just to show you that it's a concrete like normal concrete, here is alkali activated material, or if you like to call it geopolymer concrete. So it is fluidable, it can pump easily. So we tested for the setting time, for the slump, for the workability. We had the slump test. And then it is very similar to normal concrete. So it is not something weird. It is like normal concrete. It has aggregates, sand, whatever you have as a backbone of your concrete. And then, yeah, here is the concrete in the mold. After almost 45 minutes, is it still workable? And I could fit it in the mold. And then the setting time is a challenge when you use alkali activated materials, because the activation is very fast. If you don't use any admixture to control the setting time, it sets very fast. I can say 10 minutes. So it is good for example, for shotcreting or for repair of concrete, if you don't want to introduce any admixtures. But for normal concrete, we typically use at least 1.5 hours, because we are supposed to produce it in a plant and then transfer it by trucks to the construction site and then pump it in a desirable area. So we need to introduce some chemicals, some admixtures. For example, initially we introduced some superplasticizer, and we figure out that if you introduce superplasticizer, that is typically for workability cases, we could retard the setting and then get longer time for working with the concrete. And then the slump loss is another problem. So when you develop alkali activated material and then test it for the slump test for the workability, you can see that it's perfect, as you can see in the video. But after some minutes, after half an hour, after an hour, you see that you have a slump loss. It means that initially, for example, you had 7 inches of slump, and after half an hour, it's gonna turn into 0 slump. It means it hardened very fast, and you cannot work with it, for example, after half an hour. So we definitely need some admixture to, if you want to work easily and then pump it in the concrete elements. So some chemicals could help us. So initially we use polycarboxylate superplasticizer, but we are working on new types of admixtures that is more effective and cheaper than these type of superplasticizers. And then we made sure that by introducing and adding some admixtures, the property of concrete would not be sacrificed. For example, the compressive strength. As you can see, if I use 3 to 4% of admixture, the compressive strength is going to decrease definitely. But it was, for example, 7,500. It decreased to a little less than 700 if I use 4% of superplasticizer. But if I increase the percentages of admixture, it decreases to a little higher than 5,000. So sacrifice of about 2,000 psi for using 6% of superplasticizer might not be reasonable. So, but 3 to 4% is reasonable, and we can use it. But we are working on this part, working on enhancing the setting time, workability, pumpability of alkali activated materials, and different properties of this type of concrete was monitored. The durability test, for example, the shrinkage, as we expected, because the reactions are very fast, the drying shrinkage of alkali activated materials are initially higher than normal concrete. Here is a normal concrete, but ultimately the drying shrinkage is going to be almost the same. So we need to be careful about this property, the drying shrinkage of the concrete, alkali activated one, actually. But regarding the exposure of normal concrete and alkali activated concrete to sulfate attack, it depends. So if we are talking about the sodium sulfate, alkali activated materials are completely immune against the attack of sodium sulfates, but not specifically against the magnesium sulfate. So in the soil, if you're pouring foundation out of alkali activated concrete, and if you're sure that you just have sodium sulfate, it is immune. But if you have, magnesium sulfate, you need to, think more about it and find solution for that. Alkali silica reaction, you might heard about it. Fortunately, we don't have this problem in Hawaii. So we had a very good study on different types of aggregate in Hawaii. Just one type of aggregate in Hawaii Islands, Waikolua, from Waikolua Quarry, has this problem. So the problem is that some specific type of aggregate has reactive silica in it, and then over time, this reactive silica reacts with components with the alkalis inside the concrete, inside the cement. It reacts, it expands, and the concrete cracks, and cause serious problems. We can call it the cancer of the concrete. It means that we cannot do anything for our concrete after alkali silica reactions. So the initial study on the alkali activated materials show that even we use these bad aggregates, bad types of aggregate inside the alkali activated concrete, it's okay. But we need to do it over time. So it's the test that says alkali activated materials are okay if you use bad aggregates regarding ASR is just after 14 days. So we have another types of ASR tests over longer period of time. For example, 1 year that we have to do it. We have to redo these tests and make sure that and confirm that yes, alkali activated materials are immune against ASR if we use bad aggregates.
What island is Waikoloa?
Waikoloa, I think Hilo, right, Dr. Shen? Oh,
Yeah.
you're mute.
Yeah, it's in Big Island.
A big island, yes.
Yeah, yeah.
Okay.
Yeah, thanks. But for the creep test, it's good to know that the creep after 3 months, if, for example, imagine this, we wait 3 months for our concrete elements. So the creep problem is that over time, we have excessive deflections. For example, we are pouring a concrete beam on top of the elevators. And then over 3 months, we cannot open and close the door of the elevator. It means that we need to calculate for the excessive deflections of our concrete elements over time. This graph says that if you wait almost 3-4 months for concrete elements that we fabricate out of alkali activated materials, it's enough. And over these 3 months, nothing very bad happened. But for normal concrete, even after 5 years, your deflection is going to be double. If you calculate for the instantaneous deflection, for example, 1 inch for your beam, this 1 inch will increase to 2 inches after 5 years. And it's going to be problematic. But for alkali activated concrete, it's safer, at least after, for example, a couple of months, you can say that you can install your, for example, elevator. After all of these studies, we generate a schematic, flow chart for our mixing design and mixing procedure. So we have to know the type of waste material that we have, and then the dissolution timing, and we also use a pH meter to make sure that the pH, for example, the concentration of sodium hydroxide is enough and optimized. And then if we need to increase it, decrease it, and then we can add the aggregate. And then, as I mentioned, as a last step, we can introduce the sodium silicate solution. So as you remember, the first implementation of geopolymer concrete was in downtown Hilo in 2014. But we are You know, we send a proposal to HDOT, Hawaii Department of Transportation, and they're going to implement the alkali activated material we generated here in UH Manoa, and then use it for Farrington Highway widening project here in Oahu. Hopefully soon, maybe, I don't know, maybe next month. And then you can, you know, check it out when it's completed. But rather than what I mentioned in Hawaii, anywhere that we have structural and non-structural concrete, for example, in reinforced concrete elements for beams, columns, slabs, concrete bridges, concrete pavements, roads and sidewalks, for sewer pipes, for precast concrete slabs, for roofing tiles, wherever you have concrete, for railway sleepers, for masonry blocks, and for the waste material that doesn't have anything good in it. You can just, you know, put it inside the alkali activated concrete, and then make sure that it is encapsulated. It's you know, trapped inside the concrete and is not gonna leach out of this concrete. We can do it with alkali activated concrete. We are, you know, working on it. We are studying if you could use H-power ash inside alkali activated concrete. And yeah, here are some references that we use in our study. Questions?
Thank you, Riza. Any questions
so
for Riza? David?
No, where you say you're gonna use it here in Farrington Highway?
Yes, for the project, for some part of it is, you know, 4 lanes. I think for 1/4 of miles, they're gonna pour alkali activated concrete instead of normal concrete. Yes, Farrington Highway.
So
Yeah, right now it probably changed to Wahiwa, the ramp on H2. Yeah, so yeah, it's gonna be one of the first real application of alkali activated materials in the US, but sometime later this year. Yeah.
But it's for actually the pavement, or it's for sidewalks, or
No, it's a pavement for
pavement? Okay.
yes, the actual lanes of road on reinforcement. Yeah.
Okay. Thanks.
Yeah, thanks, David.
Okay. Other questions for Riza? Okay. Right. Just mention about the sulfate attack. You know, why do you think you know there's a such difference between sodium sulfate and magnesium sulfate? For sodium sulfate attack, it is almost immune, almost zero. But for magnesium sulfate, it's similar, even a little bit higher than normal concrete.
So the problem with you know, magnesium is the, you know, we have to look into the molecules of alkali activated materials and geopolymer concrete. So magnesium is very aggressive and ready to you know, interact with the molecules. So because when it is dissolved in water, I mean the magnesium sulfate, we have magnesium ions, and these ions is very aggressive to occupy the atoms spaces inside the molecules and then replace it very fast, and we have the degradation of the molecules. But for sodium, it is not that aggressive. And the good thing for alkali activated material is that the sodium ions is a part of our molecules. So for example, in the reaction of sodium with the chemical, I mean the fly ash with the chemicals, we have the combination of these atoms, the sodium, alumina, silica, and water. So it's a part of our what we have in alkali activated material. But magnesium is not. Magnesium is going to occupy some good parts of the you know, reactions, I mean the molecules, and then ruin it.
Yeah, yeah. And you know, we just learned from a lecture on durability last week. We learned, you know, sodium sulfate will attack will generate etching die, right?
Mhm.
So from monosulfide aluminate, because geopolymer concrete doesn't really have much AFM
Etching die.
at
Right.
all, almost at all. So we will not generate etching die. That's the reason. And but magnesium sulfate, if you attack CSH, and for our geopolymer or alkali activity concrete, we do generate some of the CSH.
Right.
Right. Yeah. If we can reduce the concrete permeability, maybe we can even limit the amount of attack by
Exactly.
magnesium sulfate. Okay.
Exactly. Yeah.
Yeah. Good. All right. Any other questions for Riza? It's very, very interesting research, very informative.
Thank
Okay. All right. Okay. If no questions, thank you, Riza, for your excellent presentation.
Thanks so much.
I think, yeah, that's it for today. I will see you on Thursday this week then.